welcome. This lecture is the second part of the macroscopic balances. This is where we are with respect to the syllabus. We are on macroscopic momentum balance. Just to get you started, again revise what we have done in the first part of this lecture on macroscopic balances, and you should be able to write the expressions for the following for a flowing fluid. So write an expression for volumetric flow rate of the fluid, write an expression for mass flow rate of the fluid, write an expression for momentum per unit volume, write an expression for kinetic energy per unit volume of the fluid, write an expression for the rate of flow of momentum coming in or going out of the say pipe or any equipment, rate of flow of kinetic energy coming in or going out, right? And then using all this we have done balance for forces, force due to momentum coming in going out, force due to pressure, and then the resulting force, and so on and so forth. So let's go forward. Hope that all these things are clear, all your concepts are clear. If not, go back, complete that part, understand the concepts, then go forward. Okay, so here is another problem. Consider that jet of water strikes the plate as shown. Right, so this is a jet of water. There is a nozzle pipe here somewhere, and this jet of water is 10 centimeter in diameter. Velocity is 8 meters per second, and it strikes this plate. And once it hits this plate, the fluid splits into two parts, goes up and goes down. Calculate the net force on this plate. You should be able to do this without looking at any of the previous things, because these are very preliminary concepts. Just to give you some hints, what you can do is think about control volume. Let's say this is the control volume just around the plate. Think of direction. This is your x direction, let's say, and this is y direction, let's say. Z direction we don't have to worry about, perpendicular to the plane of the screen. So find the force on the plate. Here's the solution. If you think about this control volume, and let's say this is our x direction, then momentum enters this control volume in the x direction. Momentum is not leaving in the x direction. Momentum is leaving only in the y direction. So the rate of entry of momentum in this control volume is because of this volumetric flow rate. It's pi by 4 multiplied by diameter 0.1, 10 centimeters 0.1 square, 8 meters per second. That's the volumetric flow rate. So this is our Q. And this is our rho into V, momentum per unit volume. So you'll find that the force arising out of this momentum entering is 502.66 newtons. Momentum is not leaving in the x direction. So there is no in minus out. Out is 0 in x direction. In y direction, flow is splitting into these two parts, going upward and going downward. There is no entry in the y direction. So for the y direction, momentum entering is 0. Momentum leaving, positive y direction and negative y direction, is just going to cancel out. So there is no net force in the y direction. There is only force in the x direction. Okay, so you should have got this yourself. Now let's just think about some applications. So this seems to be a childish kind of exercise, a jet hitting a plate. Imagine that this plate is a part of a turbine. Imagine this plate is a part of a turbine. Let me just take out these red things. Yeah. Imagine this plate is a part of a turbine, and this turbine is rotating. Why do we use turbines? to generate electricity. So in a hydroelectric power plant, you will have a turbine, you will have a water jet hitting the blades of the turbine, which is making the blades rotate. And then blades rotate, it rotates rotates coil inside a magnetic field, and then that's how we are generating electricity. So so if you would like to just clarify, imagine this is the turbine and these are blades of the turbine, and water jet is hitting this turbine. So we are looking at only one such blade and the jet coming, and that's going to make this turbine rotate in the clockwise direction. And if this is connected to an armature where there is a coil and it is rotating inside a magnetic field, then it will generate electricity. So that's how these hydroelectric turbines work. We generate power from the momentum of the water. Now if you think about this situation, jet is coming, jet is hitting this plate, and this plate also is rotating forward because the turbine is rotating. So at one instant, if we see, let's say jet velocity is Vj and the plate, let's say plate velocity is Vp. Plate velocity is Vp. Okay. So now the force because of water hitting this plate is going to make this plate rotate, and the force on the plate multiplied by the displacement or distance or velocity per unit time, if you displacement per unit time, that's velocity, that will tell you the power that this one such blade would generate. And then this power is what is coming to us as electricity. So what we would like to do is write an expression for force that is acting on this plate now that this plate is moving with a velocity Vp. Let me just rub this. So this plate is no longer stationary. Let me just write that. So this plate is moving to the right with a velocity Vp now, and the jet velocity is Vj. Obviously jet velocity has to be more than the plate velocity, only then the jet will hit the plate and plate will experience a force, and then power would be generated. So what we would like to do is write an expression for the force, multiply that by velocity of the plate Vp, and then we will get an expression for the power that this one such blade would generate in terms of dj, vj, vp. And then once you get that expression, I would like you to find out at what value of Vp the power delivered by the fluid to the turbine blade will be maximum, because that maximum electricity we would like to generate. Okay, solve this for yourselves, then only go forward. Pause the video. Okay, so if you have solved this problem, here is the situation again. There is a plate. This plate is moving with a velocity Vp, and a jet is striking at a velocity Vj. And our control volume is like this. I will show you the control volume in a different color. Okay, this is our control volume. So if you want to find the force, what we need to do is find out the momentum per unit volume of the fluid entering the control volume and the rate at which fluid enters the control volume. If you think of a totally different situation, think that you are trying to you're late for a lecture and your train that you are catching is just about leaving the platform and you're late for the lecture. So what do? You run. So imagine that this green control volume is your train. This train is going at a velocity Vp, if you like, and you are running at a rate Vj, and let's say there are the only way you will be able to get inside this train is if Vj is greater than Vp. That means your velocity relative to the train velocity is what matters when you are trying to catch the train. If you are running at the same velocity as the train, obviously let's assume that train is not accelerating, right? So train is going at constant speed. If you are running at the same velocity as the train, you would not be able to catch the train. You would not be able to go near the door of the train. Only if you are going at a velocity faster than the train velocity, then you will be able to go towards the door and then enter through that door, and then that's how you will enter into the train. So if this green is a control volume, the rate at which fluid enters will depend on the relative velocity Vj minus Vp. Think about this. The volumetric flow rate would be pi by 4 multiplied by dj, diameter of the jet, square, multiplied by Vj minus Vp. That is the volumetric flow rate entering this control volume, the train if you like. And how much momentum is this water carrying? Momentum it is carrying is density multiplied by the relative velocity. And that's only the extra momentum that it is carrying. That extra momentum it is carrying is what is helping you to generate the power. So force would be pi by 4 dj square multiplied by velocity of the jet minus velocity of the plate, and momentum per unit volume rho multiplied by Vj minus Vp. And power would be now force multiplied by the plate velocity. So pi by 4 dj rho, just bring this rho here, Vp, and Vj minus Vp the whole square. Now obviously if the plate velocity is 0, power delivered would be 0 because it is Vp. Plate is not moving. The force is not doing any work. It is not helping us to generate power. It is not rotating the turbine. If Vp is equal to Vj, then there is no net force because water is not entering relative to the control volume. Water is not hitting the plate. So then again the net force is 0. So if you plot in terms of Vj by Vp, so this should be, sorry, make a change. This should be Vp by Vj. Make that change. Sorry about that. Typing mistake. It is Vp divided by Vj. So if Vp is 0, power is 0. If Vp is equal to Vj, that means Vp by Vj is equal to 1. Then also power is 0. Then also power is 0. There is no net relative momentum that the water is carrying with respect to plate. Right? In between, it will do something like this. I would like you to find out at what Vp by Vj is this power maximum. How do I get that? We get that if we differentiate this expression for power. If we differentiate this expression for power with respect to Vp and set that derivative Vp dp by dVp equal to 0. So this also should be Vp by Vj. Okay, make that correction. Okay, so differentiate P with respect to Vp using this expression and equate it to 0. That will tell you where this maxima is. Do that for yourself. Once you have done, pause the video, do it for yourself. Once you have done, then only go forward. So the curve looks something like this. Okay. Find maximum power, differentiate dP, differentiate the power P with respect to Vp, set that equal to 0. So simplify, what you will find is that Vp, when it is equal to Vj by 3, that's where the power is maximum. That's where the power is maximum. So all turbines, hydroelectric turbines, are designed for this velocity, Vj by 3. They are made to rotate at this velocity so that the power delivered by the fluid to the turbine is maximum. In short, we will be able to get maximum power out of that turbine. It's important for design of wind turbines as well. Wind turbines behave in a slightly different manner. Uh, Depending on the time, we will see that. But definitely turbines in a hydroelectric power station. Okay, can we go forward? Now think about, what if this velocity profile is not uniform? Okay, so imagine that there is a flow. Let's say there is a pipe here, and there is flow. The velocity is not uniform. Velocity is maximum here at the center of the pipe. Oh, now this is again cylindrical coordinate system. That's why we have been looking at cylindrical coordinate system. Z is along the axis, R is away from the axis, and theta is a direction around the axis. Around the axis. Now, so flow is in the Z direction. Flow is along the axis. Maximum flow is at the center at R equal to 0. The radius of the pipe is capital R, which is described by a coordinate R equal to small r equal to capital R. That describes the wall of the pipe. Okay. And let's say profile is like this. So this velocity profile is difficult to measure. We'll see some methods to measure, but right now it's difficult to measure. But average velocity in the pipe I can easily measure. I can take this pipe, collect water coming out of this pipe in, let's say, 5 minutes, 2 minutes, 1 minute, and so on, and measure the volume of water collected. Volume of water collected in 1 unit time, that's nothing but flow rate, right? So flow rate I can measure very easily, volumetric flow rate, divided by the cross section. That's going to tell us the average velocity. Okay. Now, if we have to write the rate at which momentum going out, we can write that easily in terms of V average and R. Do that. Now, rate at which momentum goes in this pipeline, rate of flow of momentum, in terms of average velocity I want you to write. Don't worry just now about velocity is not average, velocity is changing. Right? Write in terms of V average and R, rate of momentum and rate of kinetic energy, rate of flow of momentum and rate of flow of kinetic energy. Write that in terms of R. By now it should be coming like this. Okay, rate of flow of momentum would be volumetric flow rate multiplied by momentum per unit volume. Volumetric flow rate is nothing but pi r square multiplied by rho, and this V average, and this V average from here you will get V average square. Rate of flow of kinetic energy, Q multiplied by half rho V average square. If I rearrange, it will be half pi r square rho V average Q. The question I am posing is, are these quantities correct? Is this a correct expression? Because velocity is not same throughout. When we say V average, what we mean, we have been using it like this jet. You see, we have been doing pi by 4 d square Vj multiplied by rho Vj, as if the velocity everywhere is 8 meter per second across this cross section of the jet. But now the velocity is not the same at velocity is different at different location. It is not the same everywhere. These arrows that you see, they are called as velocity vectors. So velocity vector means this is the direction, and the size of the arrow tells you the magnitude of the velocity. So the magnitude of the velocity is highest here, magnitude of the velocity is lower here, magnitude of the velocity is lower here, magnitude of the velocity is still lower here, and this pink curve is just a locus of points joining all these velocity vectors. So that tells you the velocity profile. Direction is the same, but magnitudes are different. Is it correct to multiply this q by rho v average when we know that this v average is not constant across the cross section? The velocity is changing. That's the question I am posing. Think about this. So here is the answer. In laminar flow, the velocity profile is Vz at any r. Vz at any r is Vmax into 1 minus r by r the whole square. I want you to write expression for flow rate in terms of Vz at any r. And using this relationship, find the relationship using this above expression. Find the relationship between Vmax and V average. Can you do that? What I want you to do is find an expression between Vmax, this maximum velocity at the center, and V average. Is V average, obviously V average is not the same as Vmax. Is it half of Vmax? Is it 10% of Vmax? Is it 0.8 times Vmax? What is it? What is the value? That's what I want you to write. Okay. Do this for yourself, then only go forward. Pause the video. Okay, so if you have done that, imagine this pipe again. This is our outer pipe. This is the wall of the pipe. We are taking a differential element at a location r, just like when we did when there was a centrifugal force, centrifugal field. Differential element thickness is dr. Now Vz is perpendicular to this control volume. It is going into the plane of the board, into the plane of the screen. So can I write an expression for the volumetric flow rate in the, because of velocity in the z direction, volumetric flow rate in the z direction, through this control volume dr? If you do that, and then we have to add up all such control volumes. So flow rate would be 2 pi r Vz into dr. 2 pi r Vz into dr would be the volumetric flow rate through this control volume of size dr. If you would like to think this 2 pi r, if you want, that's why we did engineering graphics. If you take this control volume, let's say cut here, okay, and stretch it out, what you will see is you will see a rectangle like this. This distance is 2 pi r and this distance is dr. This is 2 pi r. Length of this rectangle is 2 pi r. The height of this rectangle is dr. And Vz is going perpendicular in this rectangle. So volumetric flow rate in this differential element would be Vz multiplied by the cross-sectional area of this rectangle. Cross-sectional area is 2 pi r into dr. That's the cross-sectional area. 2 pi r into dr. That's the cross-sectional area. Multiplied by Vz would be the volumetric flow rate into that control volume. And net flow rate going in the pipe would be just addition of all such control volumes. So integrate from 0 to r. Remember, it is not minus r to r, because this is the center of the pipe. The radial coordinate r is going away from the center of the pipe. So r is in here, r is here, r is here, r is here. The wall of the pipe is described by r equal to capital R, small r equal to capital R. That's why this integral is from 0, center, to wall of the pipe. Okay, so now Vz we can substitute. Vz we can substitute from here. And you can integrate. Pause, do this for yourself. Once you're done, okay, now go forward. So 2 pi r, Vz is Vmax into 1 minus r by r the whole square into dr. and Q I can write in terms of pi r square V average, and this we can integrate and you can get an expression for V max and V average. Pause, do it for yourself. So you will find that V average is V max by 2. Average velocity is half of, average velocity is half of V max. Right? So now tell me, now answer this question again. Now, do you think these quantities are correct if we write in terms of V average and not consider the velocity variation? Just like we have written the flow rate, can we write momentum per unit volume going into this control volume? Momentum going per unit volume going into this control volume would be rho into Vz, and the volumetric flow rate would be 2 pi r dr into Vz. So now let's go forward. Now the rate of momentum, flow of momentum is 0 to r integral 2 pi r Vz rho Vz in that differential element, and then we can replace Vz in terms of V max and 1 minus r by r the whole square. So we can evaluate this expression. This integral can be evaluated very easily, and you will find that this integral is not equal to what we had written here, pi r square rho V average square. It is not equal to. That means by taking average velocity, we have made an error. So we will write this momentum correction factor beta as the actual value of momentum going out, rate of momentum going out, divided by what we would have got by considering average velocity, as if the whole pipe had the same velocity V average. So this beta is called as momentum correction factor. And why this beta is important is because we don't want to evaluate this integral. We don't want to do it every time the velocity is changing, or every time we encounter a situation where flow is parabolic, given by this expression. We don't want to do it every time. We would rather calculate momentum from this expression and just simply multiply by beta, and then that will give us the actual value of rate of flow of momentum. So do this for yourself. Find out the value of beta. Pause the video. You will find that this value of beta is 4 by 3, 1.33. Actual rate of flow of momentum is 1.33 times what we would have got had we taken average velocity. Similarly, now rate of flow of kinetic energy, 0 to r, 2 pi r Vz, that's the volumetric flow rate into dr. Oh, sorry, this should be dr. Make that correction. And half rho Vz square, integrate from 0 to r. And replace for Vz square, that's V max cube, 1 minus r by r square, the whole thing cubed. Solve this for yourself. Find the value for yourself. And remember, sir, you can always substitute V max is 2 times V average. Again, we can define a kinetic energy correction factor, actual rate of flow of kinetic energy divided by what we would have got had we considered only average velocity. And again, this is important. We don't want to integrate every time. We would rather take average velocity, which is easy to measure, calculate the kinetic energy from here and multiply simply by the correction factor, kinetic energy correction, and then we'll get the actual velocity, actual rate of flow of kinetic energy. Do it for yourself. Pause the video, and once you do that, you will be able to find the value of the kinetic energy correction factor. You will find that the kinetic energy correction factor is 2. So all I have to do is, if the flow is laminar given by this velocity profile, I just have to calculate the rate of flow of kinetic energy from the average velocity multiplied by 2, I will get the actual value. So obviously the values of beta and alpha depend on what the velocity profile is. So here is another problem for you. If the velocity profile is like a turbulent flow, so Vz is Vmax into 1 minus R by R, whole thing raised to 1 by 7. Find values of V average by Vmax, find the value of momentum correction factor, find the value of kinetic energy correction factor. And we are going to need this a lot in our course. Okay? Do this for yourself. Pause the video. Do it for yourself, then only go forward. You will find that this, so I'm telling you the answers now. You will find that this V average by V max is around 0.8. This beta is around 1.03 and this alpha is 1.06. That means if we take kinetic energy, if we calculate the rate of flow of kinetic energy from average value, average velocity, we just have to multiply by 1.06 and we'll get the actual kinetic energy. So just 6% error. That's because this in turbulent flow, the velocity profile is almost flat. It is like this. It is almost flat. That's why the average velocity and Vmax, there is not much difference. Average velocity is 0.8 times Vmax. So this is the velocity profile. If you want, if you can want to draw arrows, these are the velocity vectors. Average velocity is 0.8 times Vmax, the maximum velocity at the center. Do this for yourself. Okay, here is another problem. Okay, so imagine that there is a cylinder. Now the cylinder is like this. Let's say diameter of the cylinder is L. Take D if you like, and let's say width of the cylinder in the plane of the screen, perpendicular to the plane of the screen, is some W if you like, or B if you like, and there is a velocity profile. Wind is coming from this direction, velocity is U, average velocity is same. So obviously this cylinder is going to obstruct the flow, so the flow has to go around this cylinder. So if you look at the streamlines, these are the streamlines. Remember, you saw this video, this ball flow is coming from left to right, and then the streamlines deviate. Ball is causing an obstruction, so flow goes around. This is the picture that I have shown. Right? Flow is going around. I would like you to take a control volume like this, A, B, C, D. A, B, C, D. So obviously some streamlines go out, around. Okay. And we would like to calculate the force acting on this cylinder. And several things related to that force. And to help you get to the final answer, I am asking you some intermediate things to be calculated. Actually, this was a question in one of the mid-sems. Okay. Let's consider pressure throughout to be 1 atmosphere. So pressure force is negligible. Consider control volume ABCD as shown in the figure, right? Previous slide. Such that this AD is equal to BC is 2L. That means this AD is same as BC is same as 2L. 2 times the diameter, LL, and velocity profile is like this. Why we are considering 2L is because the velocity is reduced here and velocity recovers by the time it recovers to the value, original value U, by the time you travel a distance L in this direction and you go distance L in this direction. So beyond 2L, the velocity is as if the velocity is unaffected by this flow. Go back in this video, see the streamlines around that ball. At some distance away from the ball, the streamlines are practically not affected by that presence of that ball. Okay, so here is what I would like you to calculate. Again, now velocity profiles are changing, velocities are not same, so we will have to integrate the expressions for, we'll have to consider a small control volume and then write expressions for momentum going in, momentum coming in, going out from small element, and add up all such elements and get the total rate of flow of momentum. Okay, so remember, that's what the meaning of this integral is. Okay. Now just to get you to the last point, calculate the following things. Let's say W is the length of the cylinder perpendicular to the plane of the screen. So first thing I would like you to calculate, what is the flow rate of the liquid or a fluid in general entering and leaving the control volume through planes AD and BC. Look at the plane AD, this is the plane AD and this is the plane BC. What is the flow rate entering through AD? What is the flow rate leaving through BC? Calculate that. Once you calculate that, obviously you will find that flow rate going out through BC is not the same as flow rate entering AD, and that means there is a net flow, or there is a flow rate leaving this plane AB and DC. I would like you to calculate that, calculate an expression for that. Okay, so what is the flow rate of liquid entering and leaving the control volume through plane AD? It enters through plane AD, it leaves through BC. So that means liquid will leave at a certain rate through the control volume through planes AB and DC. What is the value? Now write the rate of entry and exit of momentum through planes AD and BC. Remember, we are considering forces in different directions. If you are thinking about this as the, if you are considering this as the X direction and this as the Y direction, we are writing momentum entering and leaving in the X direction. Momentum will enter this control volume through the face AD. That would be volumetric flow rate multiplied by rho multiplied by velocity here. Momentum will leave through the face BC. That would be the volumetric flow rate multiplied by the velocity. Now the velocity is changing, so we'll have to integrate like we did for laminar velocity profile. Okay, so I would like you to calculate the rate of entry and exit to the momentum through planes AD and BC. Now in the X direction, momentum will leave because there is a net volumetric flow rate leaving through AB and DC. I would like you to write the rate of entry or exit of momentum through plane AB and DC, and we are talking about momentum in the X direction. This is the most important part of this whole syllabus. Rate of entry and exit of momentum through planes AB and DC. Even if you don't get the answer just now, it is okay. Attempt, make an attempt. That's what is important now. We will see more details about this as we go along. So the net force acting on the cylinder now in the direction is, we can write in minus out, momentum coming in from AD, momentum leaving through BC, and momentum leaving through AB and DC. Momentum in which direction? We are writing X direction. So momentum leaving in the X direction through the face AB is nothing but rho multiplied by velocity. Velocity is u. we are talking about velocity in the x direction. Velocity is practically u in here. Velocity is not u anywhere below here or here. Velocity in the x direction is practically the velocity u in this direction, in on the plane DC or on the plane AB. So that's the momentum in the x direction and the volumetric flow rate. That's why we are writing volumetric flow rate multiplied by momentum per unit volume. Momentum per unit volume we should consider in the x direction because we are considering the force in the x direction. Okay, let's go forward. And then we are going to define the net force in a little different way. We are going to define drag coefficient. We will see how that comes about in due course. We are going to write this force divided by projected area of the cylinder multiplied by a half and rho u square. Right? So we are going to do that and get an expression for CD. So I would like you to write what this CD is. Okay. This is a hard problem primarily because this is the central concept. But if you are able to get these answers, then you should be easily able to extend it to getting all the way up to CD. Okay, you will have to get an expression for CD. Okay. So do this yourself. I don't have an answer here. I am not putting the answer here because I want you to try for yourself. Okay, you may struggle, you may not get it, but that's okay. You may think that answer is something else, actual answer is something else. It's okay. This is actually is a part of a problem from the White's book. Okay. But when we meet, we will be able to discuss this problem and we'll be able to do this problem. I'll show you the answer then. Till that time, solve for yourself, try for yourself. Okay, last point in this macroscopic momentum balance is on angular momentum. So angular momentum we are going to define as volumetric flow rate multiplied by the angular momentum per unit volume. And remember, angular momentum is if you are talking about a mass which is rotating or a mass which is going around the axis, angular momentum is mass multiplied by r multiplied by velocity. Same way, angular momentum per unit volume would be rho multiplied by r multiplied by v theta. And if you see the units, this is nothing but the torque that acts because of this tangential motion of the fluid. So imagine this is the top view of a lawn sprinkler. So this is a sprinkler, these are the arms of the sprinkler. We supply water here. This water splits into two parts and comes out. Okay, so water is coming out in the tangential direction, theta, around the axis. Axis is here, perpendicular to the screen, around the axis. So this is v theta. That's why we are talking about angular momentum. And obviously you know from experience that if water comes out, it tends to cause a rotation of this sprinkler in the clockwise direction, like Newton's third law, if you like. So what I would like you to calculate is calculate the torque required to stop the sprinkler from rotating. So imagine that the sprinkler is stationary, we are holding it stationary, and the fluid is trying to rotate it in the clockwise. So we have to supply a torque, we have to supply a force to stop this sprinkler from rotating. So here's the solution. Okay, so flow rate through each arm. So flow rate through the central part is 15.4 liter per minute. That's going to split into two parts. Right? 7.7 liter per minute will go here, 7.7 liter per minute will go here, 15.4 divided by 2. That 7.7 liter per minute will come out through this end at a velocity v. What would be that velocity? That velocity would be this volumetric flow rate 7.7 divided by cross-sectional area. Cross-sectional area is pi by 4 multiplied by this diameter square. That's the cross-sectional area here. That's the cross-sectional area here. So if you take 1.4 inch, that is 25.4 millimeters is 1 inch. 1/4 of that, we got 6.35 millimeters. So pi by 4 into 6.35 square millimeter square. Convert that to meter square. You will get velocity coming out, velocity of the water coming out as a jet through this end as 4.04 meters per second. Now we know 7.7 liters per minute is going here. That's Q multiplied by rho, density of water. R is 6 inches is this distance. 6 inches is 15 centimeter, 0.15 meters. That's our R. And V theta is now 4.04. So you'll be able to calculate the torque arising out of the water coming from here, and same torque will be from here. So it will be double. Okay, that's what will cause the rotation in the clockwise direction. But we want to find the force torque required to stop it from rotating. So sprinkler is not rotating. This is the net V theta, and therefore the net torque will be 2 times torque due to each arm. So it will be Q in each arm multiplied by rho R V theta. So the value will be 0.155 Newton per meter. It is 2 times this number. Just make a correction. 2 times this number. Q in each. So this torque is required to stop the sprinkler from rotating. If I let go of this sprinkler, don't have any torque, then the sprinkler will try to rotate. At what speed it will rotate? It will rotate such that the velocity coming out, the net velocity coming out is 0, and therefore it will rotate at a speed 2 pi Rn. 2 pi Rn should be equal to 4.04. So n will be equal to 4.28 revolutions per second or 257 rpm. So that's one application of angular momentum. You might have used some crackers which go around in Diwali, right? They go based on this principle. The fuel or the is combusted, and that is made to come out, and then that what gives rise to rotation of that firecracker. It's an angular momentum that is at work. Okay. So that's what we wanted to do in this part of the course, macroscopic balances. That's the second part of the course. The study material for this is in Fluid Mechanics 7th edition, Frank White. We are on chapter 3. We have done sections 3.1, 3.3, 3.4, 3.6. We have skipped some sections in the middle because they are not directly relevant to us. There is a section on Reynolds transport theorem. We are not going to do that just now. And then there is a section on Bernoulli equation without friction. Let's not do that. We will straight away do it with friction. And problems to solve from the book. These are the problems to solve from the book. And remember, these are the minimum problems that you should solve from the book, so that you are able to grasp these concepts. There are many problems, more than 156 problems at the end of that chapter. I am only suggesting you solve 1, 2, 3, 4, 5, 6, 7, 8 problems out of that hundreds of problems, 150 plus problems. But solve these 8 problems so that all these concepts that you have learned are reinforced and you are able to pick up those concepts. Okay. So what I am trying to say is that although we have this video goes on for about an hour, and the previous video is also about 45 minutes, so about 1 hour 45 minutes, but you have to solve these problems. That's a part of the course. That's why we have allotted 6 hours for this part of the course. 6 hours for this part of the course. Okay. So we will stop this lecture here.